Dear students, this is Debaprasad Mukhopadhyay, Assistant Professor of Mechanical Engineering, Sri Ramakrishna Institute of Science and Technology, bringing you this lecture on electrochemical machining. Electrochemical machining. Introduction. Electrochemical machining is a non-traditional machining process belonging to electrochemical category. ECM is opposite to electrochemical or galvanic coating or deposition process. Thus, ECM can be thought of a controlled anodic dissolution at the atomic level of the workpiece that is electrically conductive by a shaped tool due to flow of high current at relatively low potential difference through an electrolyte, which is quite often water-based neutral salt solution. Figure below schematically shows the basic principle of ECM. In ECM, the workpiece is connected to the positive terminal of a low voltage high current DC generator or power source. The tool is shaped and the shape of the tool is transferred to the workpiece. The tool is connected to the negative terminal. Machining takes place due to anodic dissolution at the atomic level of the work material due to electrochemical reaction. A gap between the tool and the workpiece is required to be maintained to proceed with steady-state machining. The two figures here show the initial stage of ECM and the steady state of ECM. When the electrode and the tool and the workpiece are brought closer together and electricity is passed, the steady state of ECM is reached. This is the schematic diagram of a electrochemical machining process. The tool is hollow at the center and the electrolyte is pumped through a motor-driven pump through pressure relief valve, flow control valve, flow meter, and goes through the hollow center of the tool to the space between the workpiece and the tool. The tool is connected to the negative terminal and the workpiece is connected to the positive terminal of the low voltage high current power source. The spent electrolyte, it comes down and in the centrifuge the sludge is collected and is collected in a tank. The sludgeless liquid, it is pumped again through filters to the original tank, from where the pump again sends it for circulation. This is the total electrochemical equipment. The process. During ECM, there will be reactions occurring at the electrodes, that is at the anode or workpiece, and at the cathode or the tool, along with within the electrolyte. Let us take an example of machining of low carbon steel, which is primarily a ferrous alloy mainly containing iron. For electrochemical machining of steel, generally a neutral salt solution of sodium chloride is taken as the electrolyte. The electrolyte and water undergoes ionic dissociation as shown below as potential differences apply. This figure gives us the stage-wise ionic and chemical reaction. Ionic and chemical reaction that occur when iron is being machined in NaCl as electrolyte. Fe dissociates into Fe++, releasing 2 electrons. NaCl dissociates into Na and Cl. H2O, it absorbs the 2 electrons, free electrons, and becomes hydroxyl ion, and hydrogen gas is generated. Fe ion combines with 2 hydroxyl ions to form ferrous hydroxide, and then ferrous hydroxide further combines with oxygen in the air and becomes FeOH3 and deposited at the bottom of the tank as sludge. So the total equation becomes 2Fe4H2O plus O2 to FeOH3 plus H2. H2 is liberated. The salt is not being consumed and acts as the carrier of electricity only. Current of 1000 amps would dissolve 15 grams per minute and generate H2 at the rate of 300 cm³ per minute. Applications: ECM technique removes material by atomic level dissolution of the same by electrochemical reaction. Thus, the material removal rate or machining is not dependent on the mechanical or physical properties of the work material. It only depends on the atomic weight and valency of the work material and condition that it should be electrically conductive. The CCM can machine any electrically conducting material irrespective of their hardness, strength, or even thermal properties. Moreover, as ECM leads to atomic level dissolution, the surface finish is excellent with almost stress-free machined surface and without any thermal damage. ECM is used for die sinking, profiling and contouring, trepanning, grinding, drilling, micro machining. Here one can see that the workpiece is formed in the same manner as the tool is shaped by this process. This is a die sinking operation. Then there is 3D profiling of a aerofoil section, which can also be generated with the help of electrochemical machining. This is the picture of the tool, hollow tool. The electrolyte comes and it is being forced out through the space between the tool and the workpiece, and drilling operation takes place like this. Advantages of ECM: the material removal rate is high compared to conventional machining process for high strength, temperature resistant materials. Residual stress is low. Surface finish is to the tune of 0.2 to 0.8 microns. Tool wear is nearly absent. Very thin metal sheets can be worked without distortion because there is no mechanical force coming on the anode, and so very thin metal sheets also can be machined with the help of this process. Disadvantage is that the specific power consumption is much higher than conventional machining because electricity is the main source here, and non-conducting materials just cannot be machined. Corrosion and rusting of ECM equipment is a big hazard because of the involvement of saline sodium chloride solution and all. Now we shall try to go into a video lecture to see how the machine operates.
Electrochemical machining process. Electrochemical machining, or ECM, is a method of removing metal by an electrochemical process. It is normally used for mass production and is used for machining extremely hard materials or materials that are difficult to machine using conventional methods. Its use is limited to electrically conductive materials. This video will cover the following about electrochemical machining process. 1. Working principle. 2. Construction. 3. Working. 4. Applications. 5. Advantages and disadvantages. Working principle. Whenever the two electrodes, anode which is connected to positive terminal and cathode which is connected to negative terminal, is immersed in an electrolyte, such as NaCl. When the voltage is applied across the two electrodes, the material removal from the anode starts. The anode and cathode is placed very close to each other without touching. In ECM, the material removal takes place at atomic level, so it produces a mirror finish surface. ECM working is opposite to the electrochemical or galvanic coating or deposition process. Let us understand the chemical reaction taking place in this process. As the potential difference is applied across the electrode, the movement of ions starts in between the tool and workpiece. The positive ions moves towards the tool and negative ions move towards the workpiece. At cathode, the hydrogen ions takes electrons and gets converted into hydrogen gas. In the same way the iron atoms comes out from the anode which is workpiece as Fe++ ions. Within the electrolyte, the sodium ions combines with hydroxyl ions and form sodium hydroxide, and ferrous ion combine with chloride ions and forms ferrous chloride. Also iron ions combine with hydroxyl ions and form iron hydroxide. In the electrolyte, the FeCl2 and FeO2 produced and gets precipitated in the form of sludge and settle down. In this way, the material is removed from the workpiece as sludge. The various reactions taking place in the electrochemical machining process are as follows. Construction. Electrochemical machining setup consists of following parts. Power supply. It requires a DC power supply for machining purpose. Electrolyte. The electrolyte has three main roles in the ECM process. It carries the current between the tool and the workpiece. It removes the products of the reaction from the internal electrode gap, and it removes the heat produced from the passage of the current. Tool. Tool is a replica of the shape required on the workpiece. Tank. This holds the electrolyte in which the tool and workpiece are immersed. Workpiece. Workpiece holding table. Pressure gauge. It shows the pressure at which the electrolyte is supplied to the tool. Flow meter. It shows the rate of flow of electrolyte to the machining area. Flow control valve. This helps in controlling the rate of flow of electrolyte. Pressure relief valve. In case the pressure in the supply lines increase, this pressure relief valve opens and bypasses the electrolyte to the tank. Pump. Pump helps in circulating the electrolyte. Reservoir tank. Stores the electrolyte. Filter. It helps in filtering the impurities present in the electrolyte which may chock the supply lines. Centrifuge. It helps in separating the slug from the electrolyte. Slug container. Stores the slug produced during the machining process. Working of electrochemical machining. First, the workpiece is assembled in the fixture and the tool is brought close to the workpiece. The tool and workpiece is immersed in a suitable electrolyte. After that, a potential difference is applied across the workpiece, which is anode, and tool, which is cathode. The removal of material starts. The material is removed in the same manner as we have discussed in the working principle. Tool feed system advances the tool towards the workpiece and always keeps a required gap in between them. The material from the workpiece comes out as positive ions and combine with the ions present in the electrolyte and precipitates as sludge. Hydrogen gas is liberated at the cathode during the machining process. Since the dissociation of the material from the workpiece takes place at atomic level, so it gives excellent surface finish. The sludge from the tank is taken out and separated from the electrolyte. The electrolyte after filtration again transported to the tank for the machining process. Application. The ECM process is used for die sinking operation, profiling and contouring, drilling, grinding, trepanning and micro-machining. It is used for machining steam turbine blades within closed limits. Advantages. Negligible tool wear. Complex and concave curvature parts can be produced easily by the use of convex and concave tools. No forces and residual stress are produced because there is no direct contact between tool and workpiece. An excellent surface finish is produced. Less heat is generated. Disadvantages. The risk of corrosion for tool, workpiece, and equipment increases in the case of saline and acidic electrolyte. Electrochemical machining is capable of machining electrically conductive materials only. High power consumption. High initial investment cost. If you are new to ADTW, subscribe our channel to get all latest updates from us. And click on the like button if found this video useful. Also, if want more videos like this, then support our work by sharing our videos with your friends.